But IGCC, oxy-burn are new technologies. You cannot retrofit an existing coal plant and make it an oxy-burn plant. It's better to build all new. In the meantime, we're building very rapidly coal plants. These coal plants, let's say in the United States, are a couple $1 billion apiece, and they will last for 50 years. And by the time it takes you to demonstrate these technologies, to actually get it out there, drive the cost of those plants down, it could be 10, 20 years. So what we need also, we should do this. We should experiment with these, try to drive the price down. I'm all for that. But boy, do we need something to capture at the stack, because in those 20 years, more and more billion-dollar coal plants are going to be built around the world. And once you build them, you're going to use them. So it's very important we need research to capture at the stack. Wind is going very well. It's gone down by more than an order of magnitude. It's within 20% of competitive if you discount the distribution costs and the fact that it's transient. This is a very big windmill. It's humongous. It's a 6-megawatt generator. To give you a feel for how big this is the wingspan of a 747-400. The wingspan is one of these babies. Okay? This captures 5/6 of the theoretical maximum possible energy you can capture from wind energy, these very big windmills. So they're very efficient. This is a map of the wind resources in the United States. The good news is we're very rich in wind resources. Even better news, the wind is where the people aren't. The bad news is the wind is where the people aren't. So you're going to have to ship this wind energy all over the United States. Now this map is low resolution, so it doesn't capture the wind resources around the Beltway, Washington, D.C. But in any case, we need probably an overlay, at best 25% transient renewable. You're stuck there because the rest of it has to be base load until you figure out a way to store it. And even at 25%, you need to distribute this from sites all around the country. It can't just be a localized site. This is a graph you just saw before of the learning curve of silicon photovoltaic generation from 1976 to 2003. This is the price going down exponentially. It's a Moore's law curve. And plotted here is the cumulative deployment. If you deploy more, you drive down costs. And so where do you need to be? Well, you need to be, this line is where fossil fuel energy is today. And you need to be at least a factor of 5 lower expense in generating electricity to make it useful for a utility company, again discounting the fact that it's going to be in far off places and it's transient. And so that really defines the challenge. So we need transformative solutions. I'm going to skip what a transformative, well, I won't. Very quickly, a transformative solution is the following. Vacuum tubes were used by AT&T for long-distance communication, and it was very important that AT&T make these tubes last as long as possible. They invested most of their physical science research in the 20s and 30s in making the vacuum tubes live longer, but they had a little skunk works operation to try to develop a solid-state vacuum tube, and that was it, the transistor. It took 9 years to develop, but it transformed the industry. It created new industries, the integrated circuits, the computer industry, the internet, you name it. Great wealth, but it was a transformative technology. It wasn't making the vacuum tube better. So things like a Gretzel cell, things like nanotechnology, wet chemistry, polymer-based photovoltaics what we will need in order to get that factor of 5.